If you are in high school in India right now, you know the pressure. At the end of 10th grade, you're forced to pick a strict lane: PCM, PCB, commerce, or arts. You are told that you must either be highly logical or highly creative, and that these two paths never cross. The reality is that modern crises like climate change, urban overcrowding, and extreme resource depletion do not neatly fit into a single textbook. When we try to solve these massive, multifaceted challenges using only one academic viewpoint, the resulting solutions are often clunky, hard to scale, and disconnected from what humans actually need to survive. To find a better way, we can look at a research and development lab that has been running continuous tests for 3.8 billion years: nature. Biomimicry is the practice of observing how organisms adapt and copying those exact survival strategies. Nature doesn't separate physics from design. To build practical solutions for today's world, we need to move beyond the artificial walls of high school subjects and adopt this deeply integrated blueprint. This integrated approach is called FUSIONSTEAM. Instead of studying science, technology, engineering, arts, and mathematics in isolation, we blend them together to analyze and replicate biological marvels. Take the humpback whale. How did the prominent bumps along the edge of this animal's fin end up improving the efficiency of modern wind turbines? We start by applying a mathematical lens. Mathematicians analyze these bumps, known as tubercles, measuring their exact spacing, size, and the specific geometric ratios that dictate how water moves across them. The numerical data reveals exactly what happens to the water. By flowing cleanly through the channels between the bumps, the fin reduces drag and increases lift. These fluid dynamics translate into formulas, becoming an algorithm to build an artificial fin. Without this mathematical rigor, these biological efficiencies remain difficult to measure and nearly impossible for us to replicate accurately in our own technology. Raw data on a page cannot build a physical structure. We have to apply an artistic lens, where visualization, aesthetics, and human-centered design translate those numbers into physical space. The architect Antoni Gaudí understood this translation over a century ago. He observed that nature built structures capable of bearing massive weight using minimal material. Gaudí applied those natural algorithms to his architecture, designing the towering spires of the Sagrada Familia to mimic the efficient, branching load distribution of a forest, satisfying both structural physics and human emotion. Artistic practice makes the abstract math tangible. Whether it's drafting the sweeping curves of a building or visualizing the Fibonacci sequence expanding inside the chambers of a nautilus shell, the arts turn geometric logic into intuitive form. Finally, we apply the engineering lens. Engineers take the fluid dynamic equations and the structural 3D models from the arts, and they begin to prototype, test, and iterate physical products, like manufacturing a scaled-up biomimetic wind turbine blade. This interplay creates a specific synergy. Mathematical precision provides the logic, artistic modeling ensures the design is intuitive, and engineering allows the concept to be tested and scaled for use in the real world. There is a persistent myth that technical fields lack creativity. In reality, the most advanced scientific problem-solving requires a deeply artistic imagination. When we combine these skills to study nature, we learn what biologists call life's principles. Biomimicry teaches us how to operate using current sunlight, how to recycle all waste, and how to build using local, readily available materials. We see these principles working everywhere. By analyzing the microscopic, interlocking scales of shark skin, researchers calculated the fluid dynamics required to manufacture synthetic, drag-reducing coatings for ships and airplanes. Or consider how examining the tiny, stiff hooks of a common burr plant led directly to the engineering of Velcro, creating a reusable fastening system that entirely eliminates the need for harsh chemical adhesives. Because these designs are based on biological efficiency, they often require less energy and fewer raw materials. They provide the blueprints for building a circular economy, which is critical for addressing global resource scarcity. By copying the resilience and zero-waste loops of a natural ecosystem, human engineering stops extracting from the environment and starts existing in balance with it. You do not have to shrink your abilities to fit inside a single academic stream. Your capacity for strict mathematical logic and your talent for vibrant artistic expression are meant to be used together. The world needs thinkers who can cultivate a transdisciplinary mindset. We need people who can take the analytical rigor of a mathematician, combine it with the human expression of an artist, and hand it to the practical hands of an engineer. Pursue a fusion of these disciplines, observe the mechanics of the natural world, and apply those